Alright, so this is going to be a supplemental section. We're going to talk about the major theorems from chapter 16. It's going to be about a 3-video lesson, and the videos will be relatively long. The examples take a while. So let's get started. Alright, so our 4 major theorems that we had from chapter 16. We had the fundamental theorem of line integrals. That was the first one. We had Green's theorem. We had Stokes theorem. And we had the divergence theorem. So what I kind of want to do is I want to take this back to give you a little more understanding of what's actually happening with all these things. I want to take you back to the general idea behind calculus and ABBC, stuff that you technically learned in probably the AB portion. Might not be until Calc 2 if it was in college, but still the AB portion of ABBC. The general idea was that if we had an integral, some kind of a defined definite integral, that we would take the integral of some kind of a function where it was some kind of a derivative. It didn't have to be notated as a derivative, but it was something where you had a derivative of something, because then when you take the integral, you're going to go back to the antiderivative of this, and you're going to evaluate it at the endpoints, and then subtract. So what we really did was we started off with something which was an integral, and we eventually ended up with something which was a function. Now, that function could just very well have been a constant. It could have been 7, but it's still a function. Either way, we started off with an integral of a derivative, and by using the fundamental theorem of calculus, we ended up with f of b minus f of a, which gives us some kind of a function. The key concept there is that we don't care when we're using this what happens between a and b. Only need the endpoints of the boundary. Okay, and this concept actually follows through to everything else we're going to do. So let's review the 4 major theorems, and we're not going to do them exactly the same order that I put them on the front page there. But we have 4. We got Green's theorem, and we could use Green's theorem if C was closed and positively oriented, meaning that we traversed the C counterclockwise. F would be defined as some vector field PQ, and the thing about Green's theorem is that it was 2-dimensional. And that's very important. So as soon as you see something which is not 2-dimensional, we know we're not using Green's theorem. And Green's theorem was defined to say that the integral, or the line integral, some closed, again, that's what that little circle means, closed positively oriented, of f dot dr could be defined as a double integral over the domain that's within C, that C encloses, of dq dx minus dp dy dA over the area of that domain. So again, let's think about that. We just took, if we're going to take this idea and go backwards, what you're taking is a double integral that's horrible. You're going to take a double integral of a derivative. That's what these are, right? dq dx, dp dy, those are derivatives. And we're going to end up with a single integral of a function. Because when you do f dot dr, that gives you a function. But you'll end up here, by doing this, you'll end up with a single integral of a function. That's what it's saying. I can take this double integral and end up with a single integral of a function. And when we go back to the single integral, we only care about the boundary. Right? So we took the double integral here over D, so that's all the inside of the enclosure. And when we go back, we can do this as a single integral of the line integral, which is only the boundary of this thing. So we're going from a double integral to a single integral, the inside to just the boundary. Okay, again, that's a concept that's going to hold true for all of these things. So that was Green's theorem. Then we had the fundamental theorem of line integrals. The fundamental theorem of line integrals says, and really this is one of the nicest ones, it says that if you want to take, oh, why isn't it writing now? There we go. If you want to take the line integral of f dot dr, that's the same thing as taking the line integral over c of the gradient of f dot dr, which, if this is the case and we can do it, it's just f of r of b minus f of r of a. And just to put this up there, remember that the gradient is defined to be the partials. And sometimes it's two-dimensional, sometimes it's three. And this is going to work. So this one works if f is conservative. And we had a couple different ways to figure that out, and I'll go through that stuff in a little bit. And if f is conservative, what that really is saying is that f, or this capital F, is the gradient of lowercase f. So here's the idea graphically. Remember that if we took some kind of some kind of a curve C, now this curve C is not closed, but it is continuous and has continuous derivatives. It's got endpoints A and B. And in this case, we'll just say that they go this direction. Remember, the idea was we didn't really care what happened in between here. It's just f of this value minus f of this value, and that gave us the line integral. So it's generally the same idea. Again, we're going from an integral to a function. So we start off with this integral, and we end up down to a function. Only the endpoints, only the endpoints matter in this case. All right, and then we had the divergence theorem. Divergence theorem is nice because it saves us from having to do some ugly surface integrals. Divergence theorem works if S is defined as the surface, and the surface has to be closed and outwardly oriented. Outwardly oriented. So, kind of doing a little sketch of what that looks like. Whoops. There we go. You got your three-dimensional plane here. So what you've got is you've got some kind of, oh, I'm just going to use a, that's ugly. I'm just going to use a sphere to show some kind of a man, this is horrible. Closed, outwardly oriented surface. That's better. And then you got your front and back there, just to kind of show your spherical shape. And the important part about this is that E, which is what's going to be defined under your triple integral, is the 3D space within S. So S would be like the surface or the outside of this sphere, and then E is all of the volume inside of the sphere. And the divergence theorem says that if we wanted to take the triple integral of the volume, or of the stuff on the inside, you would do that by doing the divergence of F dv. And that would be the same as the surface integral, or the double integral, of F dot ds. And again, just like before, what we're saying here is that you can take a triple integral of some kind of a derivative, because remember that the divergence of F dv is defined, the divergence itself is defined to be as a derivative because it's the cross product of del and F. And then we can end up with the double integral of some kind of a function. And that's what you get. So what we are saying is this goes from a region, E, to the boundary, S. Again, you guys should be kind of getting the idea here. Everything is going from something down to its boundary. Something down to its boundary every single time. All right, and then the last one that we had was Stokes Theorem. And to do Stokes Theorem, your surface has to be contained in C. So let's say that we had, I don't know, either the top half of the sphere or some kind of a paraboloid or something like that. Anyway, so what you've got is some kind of a surface here. Might look something like this, where this part right here is the surface. And this part right here on the bottom, it's C, and C is going counterclockwise. And your surface here, it's just the surface. It's not everything inside. It's just this surface right here is contained over some kind of a domain, but the domain here is enclosed by C. So what the Stokes theorem says is that we can take the double integral over S of the curl of F dot ds, which is the same thing as the single integral of F dot dr. Just so that we know, AACC has a tendency to write this in what we have seen this form before, but they have a tendency to write it in this form as the curl of F dot n ds, where F and n are your vectors in this case. We're going to actually, you'll see that when we go through the examples, that's going to be a common form. So again, you're taking something which is going from an integral down to a function. Over here, it's the region of the surface F, and we're reducing it down to just the boundary. Again, and remember, with Stokes theorem, it doesn't matter what the surface is if you're going to use Stokes theorem, because you literally are only going to do the line integral of this thing which encloses the surface. This surface could have been a parabola, it could have been a cone, it could have been a cylinder. It doesn't make any difference. It's just this, the boundary C, that's going to matter. All right, so here's our plan of attack. What we want to look for when we're going through these problems in order to figure this, what we're going to do. So the first thing is, if we're going to try and do a line integral, and we're given some kind of a function of x and y ds. So here's the important thing. We have this ds and we're trying to do a line integral. This is what some teachers, I've heard them call it. It's just doing this by brute force. It's just going back to the very original idea of doing an integral from a to b of f of r of t, so parameterizing our function here, and then ds, which is the magnitude of r prime of t, dt. So remember that this piece right here, r of t, is defined by your curve, so we're going to parameterize it by using our curve, and that this part right here, the magnitude of r prime of t, well, r prime is a derivative, magnitude is the square root of that, so it's the square root of dx dt squared plus dy dt squared. And this is basically, this is a way to do it. It's one of the longer ways. Some things have to be done this way. There's just not really an easier way. But that's always an option. It's not always easy, but it's always an option. So you could do it by brute force. The second way, if we're going to try to do a line integral of f dot dr. So the first thing you might want to look for is, can we do it directly? And that's what we just talked about above. So again, integral from a to b of f of r of t dot r prime of t dt. And I mean, it's tough. Some of these things, it's really, really hard just to trudge through all the stuff that you have to do to get to that. It's not horrible, but it's there. It's an option. Option B, if, and this is the important part because you have to meet the conditions, so this is the stuff we have to know, if f is two-dimensional and C is closed and positively oriented. Positively oriented. Then we can use Green's theorem. And Green's theorem, again, we'll restate double integral over d of dq dx minus dp dy dA. Green's theorem is good. It makes doing it really simple. It's very nice. Okay, C. If F is conservative. And I said we'd talk about how we figure that out in a second. So there's two ways. Two-dimensionally, it's actually pretty easy. dq dx has to equal dp dy. If that's the case, it's, whoops, what happened there? If that's the case, it's conservative. I'll get out of that. Weird. I don't know. Ah, there we go. Strange. Must have hit something, didn't realize it. So if dq dx equals dp dy, it's conservative in two dimensions. In 3D, if the curl of f equals 0, then it's conservative. And if that's the case, then what we can do, what we can say, is that f equals the gradient of f. Then we can do f of r of b minus f of r of a. This is a relatively easy method. Now you do have to be able to do your antiderivatives. And in 3 dimensions, remember, you have to deal with the whole partials backwards, but it's not too bad. It's actually one of the easier methods to do. It's one of the nicer ones. And then D, you can do Stokes theorem. Which again says that F, we're going to use slightly different notations here, would have to equal some curl of G. So what that says is you would take the line integral of f dot dr, which would equal the double integral of s of the curl of some function g ds. This one is not as easy. So if you kind of had to rank them, if you could, if this is the case, you would want to go with C first. You'd want to try and do the line integral. Green's theorem's pretty nice and easy for the most part, so that's a good one. Directly and Stokes theorem is probably not the way you would want to do it unless you have to. And sometimes they make them easy to do it that way. And remember, this is if we're trying to evaluate line integrals. Don't get that confused with the next one, because the next one is if we are trying to evaluate surface integrals. So our third thing that we're looking at is if we're trying to do a surface integral of f dot ds, which again, AACC writes it like this. Oops, that's not a D, it's an S. What am I doing? Of f dot n ds. It's the same thing, but the way they do it, they just show you that doing this ds part right here is you have to find that normal vector to dot. So again, you've got 3 different methods you can do directly. Which would be, again, kind of a pain, but it's doing the double integral over d of F of U and V dotted with RU cross RV dA. Just to remind ourselves what these things are, this right here is the parameters for S, so you're evaluating your function using the parameters of your surface, and then this part right here is the um, cross product, and it has to be oriented outward. And doing this one, like I said, this one is a pain. Sometimes it's the best method, but it can be a pain to do. If, however, S is closed, this is the nice one, then we can do the triple integral over E of the divergence of F dV. That one is easy, as I'm sure you saw from one of your last homework assignments. Or if we know that F can be written as the curl of G, then we can do the double integral over D of F, and that's going to equal the double integral of the curl of G, which is the same thing as the single integral of the over C of G. This is not often used. Not often used. I think I have one example where we might do it this way. Other than that, it's not really something that we're going to look at. So for the most part, A and B are going to be the ways to do it if you encounter example number 3 here. All right, so one more page here on this video, and then we're going to start our examples. So let's just run through, and I know we've written these things down, but I want to give you guys a nice clean sheet here to look at these things. Fundamental theorem for line integrals, Green's theorem, Stokes theorem, and divergence theorem. We're just basically going to write the conditions that you need and the actual theorem itself. So the conditions for fundamental theorem of line integrals. F is conservative. And again, you had the, whoops, stop doing that. Conservative. Weird. Which means that F can be written as the gradient of little f. And again, 2 different ways you can find that. We did list those on the other page. So the theorem actually says that the integral, line integral of f dot dr is the same thing as the line integral of del f dot dr, which is the same thing as f of r of b minus f of r of a. Again, you're just evaluating the original function that you could find at the endpoints. And you do have to go through the antiderivative process to get there. Green's theorem. Let's do Green's theorem in red, because why not? Green's theorem, C is closed and 2-dimensional and positively oriented. Okay, so, oh, I know what it is. I'm hitting this little button on my pen. That's what's happening here. There we go. Positively oriented. Now where'd the pen go? Weird. is, nope, not defined. D is bounded by C. Whoops. What the heck? And F is a vector PQ. All right, so we've got line integral positively oriented of F dot dr. This is really hard to do without the cursor thing showing up, and I don't know what happened to it. It just like all of a sudden disappeared. Wow. Equals, this is really difficult to do. All right, so I truthfully don't know what's going on here. This is going to be really tricky to do. Double integral over d of dq dx minus dp. Oh my goodness, what is going on? I'm hitting these buttons on accident and I'm not meaning to. dp dy dA. Yeah, I finished that one. All right, two more to go, and then I'm going to try and figure out what's going on with this thing. All right, Stokes. Let's see if I can figure this one out. Let's do that one in green, I guess. I don't know. So S is bounded by a closed positively oriented curve C. Man, this is tough. Double integral over S of the curl of F dot ds, oh, there we go again, equals the single integral of F. I'm not sure how I'm hitting this button all the time. dr. I'm really trying not to. And don't forget, oh, there's the curl. The curl is defined as del cross F. I'm going to have to erase that and try again. Is defined as del. Nope. 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 Why is it still doing that? Del. Wow. Cross F. All right, one more. Divergence theorem says that we have S is closed. Oh my gosh. I can't hold this pen any different. You would think it's a new pen, but it's not. It just isn't working right. It is closed and outwardly oriented. And E is within S. Okay, if that's the case, then we can take the triple integral over E of the divergence F dv, which is the same as the double integral over S of F dot ds. And don't forget that the divergence is defined as del dot F. Whew. Okay. Sorry, that took a lot longer than I intended it to. Got to figure out what's going wrong with this cursor. But that is the first video. We will come back, and I think I've got 6, maybe it's 7. Could be 8. I can't remember what it is. Um, examples for you guys. All right.